This is the second part of Chapter 5 on memory hierarchy. I'm going to pick up where we left off last time, which I put in a good transition slide here to explain kind of big picture of memory hierarchy and where we've been going, starting halfway through here, right here. So this is out of the text, and it just kind of gives a picturesque way of looking at this. That we have the CPU and then we have all these levels. As we get further away from the CPU, the amount gets larger, but because cost is decreased, as we talked about, but the latency is significant. It's more impacting. So let's talk about these lower levels, right? So here, I think I went through this last time, but here's an example given a multi-level cache. And what the CPI is of 1, and the clock rate, the miss rate, and the main memory access time. And then with primary cache, so right here, it's co-located essentially with the CPU, okay, what the miss penalty will be. And so this gives us what our effective CPI is, not because it's not because the CPI is unable to be better based on the CPU, the processor, the CPU, but it's because there's latency when it's trying to pull data based on how often, right, the 2% of the time that it misses. And here's the price we pay. So, I mean, look at where the effective CPI goes from. Pretty significant increase, even with a small percent miss rate. Here's another example now going up to L2, so that's going down, relatively speaking, further away. What happens is when you have a miss now, right, the penalty is 20 cycles for L2, whereas it was 400 cycles for primary. So, excuse me, that's a hit. That makes more sense. So a miss is 500 cycles, a hit is 20 cycles. So even just to think about here, a hit now, even going out to L2 is significantly longer in CPU cycles, or clock cycles. So big picture, putting it all together again, right? If we have some L2 and we have the extra penalty, right, we can even reduce our CPI by having more available, so we decrease our miss rate overall. So that's kind of some examples, and you really need to work through it to kind of fully understand this. I don't have a lot of time to spend on that for the time constraint we're in with this presentation. So big picture, what are some trade-offs from multi-level cache considerations, right? What are the trade-offs? Obviously, what's with principle of locality and recency, right, temporal and physical locality, you want them close and often, right? So that's what you want for your primary cache. Same considerations dominate L2 cache, but you want to focus on keeping us in L1 cache, right? And then consider hit time still has impact, but less impact than a miss. And so here's kind of the overall results and what we'll see at the end of the show, showing you some pictures of what designers are kind of settling into. There are other CPUs that can do out of order execution, and so basically trying to keep the CPU always busy, right? And so right here, effect of a miss depends on the program data flow, and so it's hard to analyze what the effective CPI is on some of these because it's kind of jumping all over the place, just keeping that CPU fed. Here are some graphs that demonstrate kind of what the trade-offs in a couple of major softwares like Radix and Quicksort, which are common sorts. A Quicksort, obviously, I think everyone has to do that going through their undergraduate program. And it kind of gives you an idea of the size of the items to sort versus the instructions or clock cycles and cache misses per item. So you can kind of look at that and consider what the trade-offs are. Okay, we're going to go into paging on virtual memory addresses because I think it flows well after understanding cache. So cache, we talk about how it has a limited amount of space and it's going out into main memory, RAM, right, and pulling information from there into cache. And we talked about how it balances and does that. Well, guess what? We've got to pull stuff sometime from hard disk, right, all the way to main memory so that it's available in main memory or RAM to later be pulled into cache. And so if you understood direct mapping with cache or part way associative or fully associative with cache, then virtual memory is very similar to that. It just uses different terms, synonymous terms. So instead of blocks, as we used for cache, in disk addressing and virtual addressing, we use pages. And it talks about it right here. So so it's not blocks anymore. They're now called pages, and they're from a set of addresses for virtual addresses and another for physical addresses. And the reasoning behind this is that here's where the twist's a little different than cache, in that in cache we're taking a sample of main memory. Well, in main memory out to hard disk, we're taking a sample again of the hard disk into main memory, RAM. But what we do is we trick the CPU and the computer into thinking that we actually have all of it available immediately. And so again, there's a price we pay for that. It's not really a trick, it's just organization. And so here's how we do that. We create an address translation, just like how we had blocks and where they mapped in cache. In memory, we have pages and their translation. And it's usually called a page table, and it holds the virtual addresses and how they map to a physical RAM address. And every program holds its own page table, and it with its virtual page number and its physical and then page offset. And so you can begin to calculate and kind of figure out what the payoff is here, right? So for example, this image right here demonstrates that if the page size is 2 to the 12th of 4 kilobytes, big B, the number of physical pages allowed is 2 to the 18th, right? Since there's 18 bits in it, okay? Thus, main memory can have at most 1 gigabyte, while the virtual address is 4 gigabytes. So RAM, we only have 1 gigabyte, but we convince the computer that it actually has 4 gigabytes by using this virtual addressing, okay? Now, that presumes that whenever up until now, as I've explained it, that we always have what we need in RAM. But just like with cache, we don't always have what we need in cache. Same thing, we don't always have what we need in RAM. So we have to deal with that. And the way we deal with that is, like I said, we have a page table on each program. And then modern RAM, what it does is creates a translation look-aside buffer where it's actually cache built into RAM, and it's keeping track of what pages we've actually pulled from the hard drive, what pages are dirty, meaning they've been updated and need to be updated out in the hard drive, if we've referenced them at all since we've pulled them, right, and if it's valid. So it looks at a bunch of different things. And the book actually gives a better picture of this. It's not in the slideshow, so I'm going to go to the book here real quick and pull it up. Let's see here. Well, this is reasonably good. There's actually another book outside of this class called Modern Operating Systems by Andrew Tannenbaum, and it has a better picture. But here's a simplified example of a page table register, right, and what's in it, the valid, the virtual page number, the page offsets, right? But there's a better picture I thought we had in this book that has the valid, not valid. There it is. Okay, so here's the translation look-aside buffer, right, where this is cache that keeps a more up-to-date reference in RAM, so we don't have to look into each program's page table to see what's there. I can give you an example of this. I had something kind of funny happen today. I needed to send a piece of information to one of my friends last night, so I texted them a reference to a book, and then when I finished, that was it. I forgot about it. Well, today, totally separate, when I was on the computer, unrelated event, I needed to send, it just so happens, this is recency, right, temporal locality, the same reference, the same book. It's like, let me see here. Now I'm doing it right now. I'm looking to find what it was. Psalm 37:23. So I couldn't remember that address and location in the book, and so I started to look it up in the book, and then it hit me today as I was writing the email. I was like, wait a minute, I sent this last night. So I went to my text, right, and I just looked at where it was, the book name and address, and then I just typed that into the email, and so it saved me a lot of time instead of looking it up in the book. And that's analogous to what a translation look-aside buffer does, right? Is it's something kept, like a current record of all the physical pages, their virtual and their tag, right, and valid, dirty, or if they've been referenced, right? And then each program keeps its own page table within its pages, referencing out to disk storage. We don't have any workout problems for this one. I'll probably go over this one with you separately when we do like a lab. But this is similar, I guess, is my bottom line point here up front to the way cache and RAM interact with each other. It's the same idea of balancing data when we need it between RAM and disk storage. So this is, in this picture, you can see the page number here is probably one of the most useful pictures and references in the text as currently we have available to us. A few last points on that. So this is what is virtual memory, right? So I kind of introduced it as we went. It's just the concept that we convinced the processor that our RAM is much bigger than it actually is by creating virtual addresses, and then we reference them. So it's analogous to blocks in cache and RAM as it is to RAM and hard disk, okay? And so because of that, we have all this extra stuff we have to do. So that takes care of previous video, cache and RAM, and now you're kind of caught up with RAM and hard disk. So let's talk about some questions about balancing this. Oh, here's the good picture there, right? Is what's useful, right? And this summary page talks about it right here. Most of what I've talked about already. Here's our balancing things, right? Where can a page be replaced in memory? Well, something to consider with translation look-aside buffer is that it's fully assuming, we can assume it's almost always fully associative because we want to use all the RAM we have all the time. Because just as you saw with going to lower levels in RAM or even cache, the cost for a miss or even a hit, right? Well, now imagine going out to hard disk, right? We're talking about hundreds times larger impacts. So thousands, 10,000s, hundreds of thousands of cycles are occurring just trying to pull something in from hard disk, right? So these are considerations, and these kind of answer the questions. So when we need to replace a page once it's filled, right, it's the same principle as cache. We look for the least recently used, so that reference bit suddenly is very useful, right, to see if it's been referenced or not. And it also depends on the hardware system of your choice. And then we have to also deal with, just like we did with cache and RAM, we have to deal with when we have to do a write back, right? When we've pulled in, so we've pulled in a virtual page from disk, we've pulled it into physical memory or RAM, and it's there, it's valid. So like maybe this one right here, right? It's valid. We haven't used it yet or written to it, but we have referenced it. But now we write to it. Well, now that becomes a 1, meaning it's dirty, meaning it's different in our RAM than what it is in disk storage because we've changed the values in it. So now that has to be written back. So depending on your system, it may write it back immediately. And that's what it says here. If you think about the cost payoff, generally you're going to want to start writing it as soon as possible. And that ought not to take cycles on the CPU. The hardware ought to be able to do that between the RAM and the hard disk. Okay, putting it all together in a big picture, right? Here we have cache, right? And this is kind of what it looks like putting everything together with the translation look-aside buffer, right? And the page table, and how virtual memory runs. So here is all the possibilities, possible combinations, excuse me, right, of the events, because now we have the TLB, the page table, and cache, right? So, you know, what's going on, right? So this talks through, I won't go through every situation, maybe I'll leave that up to you guys to look at this. You can pause it here and look at it. But here's all the combinations that can happen, you know, when we're looking for data or an instruction. Okay, and why and what we do to deal with them. Alright, so that's kind of the conclusion of cache and virtual memory. Now, there's some other ways that we can optimize how we do that. Now, given all of that former information, there's some ways we can optimize what we do. Okay, so if we can't pull in everything we need into RAM, or especially into cache, for example, the other solution is to make better use of what we have, right? So a double precision general matrix multiply, which it's said twice, so this sentence here probably ought to be fixed because it says double precision general matrix multiply optimizations. Take advantage of this. So the idea behind here is let's optimize our program to better use the space instead of you know, finding better ways to virtualize the space we have. So what this does is basically this is trying to picture out that generally when we have a double matrix multiply optimization, like multiple arrays being multiplied, generally what happens is we pull them in one row, you know, to get this corner of information. It's probably some top row times some other matrix column, okay? But this is very unoptimized, right? Because now we have to load all this in, load all that in, and it only gives us this small area of answer. So guess what? When we want to calculate this, then we need to load all of this in, blow all that away, load all the next row in, blow all that away, because presuming you don't have enough space, and now we get this, and you know, wash, rinse, repeat, so on and so forth. Instead, the idea is break it into problems, which is called blocking, not blocks, but blocking. And the idea is, why not take areas and do the math within those areas and calculate the solutions within those areas, right, of a giant set of arrays, right? Because all of this can be pulled into cache, all of this can be pulled into cache, and then we multiply. This isn't a very good picture, but we multiply, get the result, and spit all that out. Now we're completely done with these. We're never going to reference them again. So now when we pull in all of this area and all of this area, we do all the multiplication there, spit it out. Now we're never going to touch these again. So here are some examples of calculations they did to demonstrate this, right? So if your cache is limited to a 32 by 32 space for whatever word size this is, I don't know, but let's say these objects are 32 by 32. This is giga flops, so gigs of floating point operations per second, right? So floating points are a good sample because they, as you guys saw in chapter 3, require a lot of work, right? I mean, you're really using your CPU. So, and the ALU. So using floating point operations, right, in a double precision general matrix multiply are a good sample for testing this blocking optimization, right? So let's focus on this first, right? When we pulled in a 32 by 32 array and it fit into memory, right, we're obtaining roughly 1.7 gigaflops, right? Giga floating point operations per second, okay? Right, but now let's pull in a larger than what we have in memory available. So we pull in 160 by 160, but we only have 32 by 32 of whatever bytes or whatever it is. Just make something up, right? We didn't have that available, okay? So now we're larger than the area available, so that means we do this, right? We take parts of it, right, array by array, load them in, calculate, spit it out, load them in, calculate, spit it out, and so on, right? Well, you can see right here, we lose a lot of time, right? 0.2, we lose 0.2 gigaflops, right, of operation time that aren't being done per second, probably because of memory loading, right? Because it's going out, grabbing stuff, and so on. And you can see the decreasing returns here, right? Diminishing returns. So by the time we get to the 960 by 960 range, and we do the operation, whatever it is, maybe it's DGEMM again on it, right? Well, now you're only getting on average 0.8 giga floating point operations per second, right? So this is the unoptimized code. So that's doing it all this way with larger and larger arrays on the same size cache. The cache was only this big, okay? But to demonstrate blocking optimization, how valuable it is, right? So if we can re-optimize the code so it operates in blocks relative to the cache size, right? You can see here that even when we get into larger matrix multiplications, right, the processor isn't wasting its time. We get very small decrease. We go from 1.7 to 1.5. So instead of losing half of our efficiency, effectively, if you want, we only lose 0.2 of it, or a tenth of the efficiency, because the CPU or the code, however they've designed it, is automatically taking in bite-sized pieces, no pun intended, into the cache and calculating them, spitting them out, and then moving on to the next, right? So there's still some loading that has to occur, right, when we get into optimized blocking. But here's another way, essentially, to take advantage of what we already have instead of playing the memory game with virtual page. I mean, it's still occurring, but instead of depending on that, we optimize our code. And in the chapter 4 additional video, I talk about some other options like loop unrolling that would also help with things like this, okay? All right. Now, up until this point, we've presumed we're going to transition here. When we pull from memory what we pulled from where it was stored to when we read it, there's no errors and everything works well. That's called service delivered as specified, service accomplishment. Okay, it's dependable memory. Okay, sometimes though in real life, right, we get service interruption where it's different from specified service, or we have other issues like a failure. Okay, so let's talk about that, right? So that introduced, and it'll be introduced here if you take the course CS 5200 or 4200, you'll go far more into this, but basically they objectify this, and this becomes very important when you get to large scale like server farms, because you get what's called a mean time to fail, mean time to repair, and mean time between failures. Okay, mean time between failures is the sum of mean time to fail and mean time to repair, and availability is mean time to fail over mean time between failures. Okay, the book also does a pretty good job giving an example and laying this out. So I'm going to reference the book here, going to where it shows the errors right here. So it gives a pretty good example. You're going to go through this example with your peers in class, but it gives you the additional term availability. And availability is critical when you have things like a server farm, because when you have like a server farm, you want an availability of 99.999. It's called 5 nines, 9%. So 99.999%, because that means you only have on average 5.26 minutes of repair a year. Okay, so you can see how every 9 impacts your availability. Well, it's the same on a CPU. I mean, this is the same when we talked about the percent of time you get misses, right? Well, what about the percent of time you have failures or bad code that comes in? Well, it's going to impact your overall effective CPI. So you want, ideally, the best availability possible, the least time, the most time between failures, and the least time to repair when there is a failure. So this is a little caveat. The book kind of goes down this, and it's important you know it because you will use this in your future, definitely in the industry. And we'll go over examples in class. Alright, so so far we've re-reviewed on cache, talked about virtual memory and virtual pages. I'm not going to talk about virtual machines here. It's pretty common now. Most people are familiar with them. I really think that content fits better in another course. Just know that virtual machines, basically the operating system has to have some level of control, and it's called a hypervisor, deciding what level of permissions each virtual machine gets on your computer, so that obviously plays out into memory and onto the CPU. That's about all I'm going to say about virtual machines. And then just recently we talked a couple seconds ago about availability and performance. Okay, a few things left in this presentation. Let me go back there now. Talking about errors. Alright, so this is also useful, and it's introduced here is how do we detect and how do we correct errors? Well, Appendix B talked about parity. I didn't touch on it. I might add that in a future date. But parity, basically you have even or odd parity. The idea is if you have 8 bits and there are 8 ones, then you have even parity. If there are 8 bits and you have 5 ones, 3 zeros, then you have odd parity. So you can add a bit and you can detect when one of those was flipped based on this check bit to see if you were expecting even or odd parity. Okay, that's parity, and you can use it to detect errors. Okay, as it says here, right, as more time occurs, right, then you have more bit failures theoretically. If you are going to have some, the more time you have will increase its likeliness. Okay, that just makes sense from a statistics perspective. All right. Parities can be used to correct single failures. So if you have a single bit that is flipped and you don't know, and you know which one it is using parity, you're able to correct it. Well, the issue with parity is how do you know which one it was, right? If you're just doing even or odd parity, how do you know which bit flipped, which bit was incorrect? The book does a pretty good job. I'm going to go there right now, demonstrating this. You can see the picture right here, and they talk about the Hamming distance. This is in compliment to the inventor of Hamming code. We'll talk about that in a second. Basically, if you have 0, 1, 1, 0, and it's inaccurately flipped to 0, 0, 1, 1, so you can see this bit flipped, and this bit, then the Hamming distance is 2. Okay, so there's distance of 2 is what it's called. Okay, for the error that occurred there, right? Parity code, though, as we said, mostly focused on error correction, finding when one of these was flipped by adding a check bit of some sort. Okay, Hamming code is really cool because what Hamming code is focused on is error detection and error correction. The inventor figured out a way to do this, and he named it Hamming error correction code. Okay, I mean, as the book says, in honor of him. And I don't think the slides do a very good job talking about it. Here we go. Actually, this is a pretty good picture. So what Hamming error correction code looks like is it's a method to both detect and correct a couple of bits, okay, in 8 bits. So here's the algorithm, okay. So start numbering your bits from 1 on the left as opposed to traditional numbering of rightmost bit being 0, okay. Mark all the bit positions that are powers of 2 as parity. All their bit positions are used for data bit positions, 3, 5, 6, 7, 9, 10, 11, 12. So if you marked your bits, I thought the book showed a picture, kind of does, kind of doesn't. Anyways, if you marked your bits as it says here, right? 2 to the 0th is 1, so your first bit is going to be a parity bit, okay? Second bit, which is 2 to the 1st, that's 2, is going to be a parity bit. 3 is not a power of 2, so that will be used for data. 4 is a power of 2, so that's parity. 5, 6, 7 are data. 2, right? 8 is parity, not data. Okay, so it lists it's kind of confusing, but it lists the parity bits and the data bits here. Okay, and so you can figure out how that's done. So if you have 8 bits, what you do is you spread them out, right, and then introduce your Hamming code in between. Okay, using the Hamming code, after it comes down, you can do a deduction and you can find out where the error occurred. And that's what this gives an example of. I definitely will need to do this in class because I can see already it's going to take a lot of time in the video if I try to go through all of it here. But in essence, right, it gives an example going through. If we start with 0, 1, 0, 0, 0, 0, 0, 1 as our data, right? That's 1, 2, 3, 4, 5, 6, 7, 8 bits, and 1, 2, 3, 4 parity bits. Okay, right? We set these based on our data. I'll go through a specific example. And whenever this whole 12-bit package is delivered, right, we can determine based on these parity bits if the data was corrupted or not. Okay. It is still possible for it to fail if there were a significant number of single-bit errors in that single 12-bit package, but it's much less likely. And I will definitely go through this in example in class because it's going to take a long time to go through it there. Big picture, parity and Hamming. Parity is for detection, Hamming both detection and correction. Okay, we're going to transition. There's just a few more things to touch on. And then that kind of ends this presentation. So we'll go back and discuss some considerations on virtual memory. I'll use a transition here. When virtual memory first came out back in 98, 99, whenever it was started using on Windows, it was horrible. I remember it was like a big cell. Hey, it has virtual addressing. It just said virtual memory. Didn't know what that meant, but it was supposed to make Windows perform so much better. And here's what I saw as a user. There's a reason why this happened. I'll explain in a second. But what I saw is now it said I could, run programs much bigger than before, like games, and I thought this was awesome. So I went ahead and would start those games or software that were processor intensive at the time, like a word processing program or Excel or something, and I was trying to do both at once. And what happened is I would click on the game and start running it, and it would stall. I mean, it would completely lag, and the graphics would fail, and I would be sitting there waiting and waiting. And finally I got bored. I thought, well, this is loading. I'll just go back to working on my project. So then I'd go back to the project. My presumption was that I could do both at the same time and that it could load both at the same time. But that's not how virtual paging works, right? It only tries to predict or have ready the memory that we think will be used. And so what I didn't realize I was doing is actually making it worse, because I was it would basically load everything in and mark it as a valid bit, right, as virtual memory into the physical memory from disk for the game. And just as it was about to get everything loaded in, I would click on my Word or Excel program, and it would start blowing out everything from RAM that I just loaded in. And here's why. And eventually it just ended in me restarting the computer and doing one or the other, and giving virtual memory in Windows a bad name. Here's why. Essentially, when they were first figuring it out, right, is they made really large pages, right? Because when we're dealing with RAM and hard disk, we call them pages instead of blocks compared to cache. Okay, so they made really large pages, larger than 4 kilobytes. Okay, and they found out that the cost and overhead of having these really large pages was so significant, it doesn't talk about it here, that it made virtual memory not worth it. So then, you start trying this out. You try smaller pages of virtual memory and see if that works. Well, now you're constantly loading in, smaller parts of pages. So they kind of commonly settled on 4 kilobytes as a common page size that worked well. And then they also adjusted their algorithm on which pages to move and where. So it got better. What I was experiencing, right, was kind of what's called thrashing here, right, is increasing main memory size leads to more page faults, right, and because the more I thought, the more virtual memory that was identified in my translation look-aside buffer left more page faults. Page fault is where the RAM goes to check if it has loaded the virtual page into its memory and finds out it hasn't. It's got a page fault and it's got to go out and capture it. All right, and so early virtual memory schemes which didn't use it, at least recently used replacement strategy. So this was what was going on, right? Is my computer thought it had a whole ton of memory, it didn't, and it wasn't replacing the least used, it was just replacing whatever it had there. So I was experiencing thrashing, and it usually ended in restarting the machine. Okay, let's talk about, so here are some methods for dealing with that. 3 C's for misses, compulsory capacity and conflict. So let's talk about what that looks like. Here are ways, here's the performance of it, okay. Here are solutions to it, right. I'll come back to that. What I want to do is look at a finite state machine. Here is a picture of how it works, kind of a simple, that should say finite state machine, but here's a picture of how this looks. So ideally, right, we start in the idle state, okay, so a read or write is occurring, okay. So cache looks to main memory to see if it has something, okay. Main memory does a read or write, and it's a hit. So the valid bit has been set, okay, it compares the tag and the translation look-aside buffer. The valid tag is set, and we look into the program page table, it's written there, so let's say this was a read, it's a hit, so all we have to do is mark it as cache ready and send it back out, okay. It's there, okay, and then the cache grabs it, alright. What about if we have a miss, okay, or invalid block, okay? So these, or vict, we'll deal with read, write, miss, or invalid block for, I'll talk about these mostly, okay? This should say page, but anyways. So what happens is it makes the request from cache out to RAM. It looks in its translation look-aside buffer, okay? And either, right, the valid bit, it's not there when we look to the index, right, just like you would with cache, but now in the TLB, it's not there, okay, or because the valid bit's not set, or it's there, we look in the page table and it wasn't loaded in, that page wasn't loaded in. So then we have to go out and allocate and read a new block from memory, meaning from disk, okay, and then bring it in, set the valid bit, update the translation look-aside buffer, the page table for that program, oops, and write it back out to cache, right? What if we have a read or write miss or invalid dirty block, okay, so similar, except this now we're dealing with a write back, okay. So we'll deal with the write miss. So we've been doing work in the cache. We look to write something, some result, out to RAM. RAM writes it, but then looks to see if it has that location, doesn't have that location to write it. So it needs to treat it as if we're going all the way out to fetch a read. It goes all the way out and writes it back to hard disk. When it's finished writing, we get the allocate, and then the allocate says memory is ready, so it's been updated. Update the TLB again to say not dirty anymore, and then it goes back as a cache hit for cache itself. So a lot to do. I kind of put this last because it's a good picture of kind of seeing how it all works together. And that's one solution. Dr. Glock kind of made a reference, and the book does here. There are some more advanced ways to do this, right? We could divide these into different states and try to do more stuff in parallel. So that kind of brings everything together in a picture of how it works. Now I want to talk about the fixes, now that you've kind of seen how it works, right? And there are drawbacks. This is a trade-off diagram, right? So if we do a design change on this process, right, and we affect the miss rate, right, so we have a least miss rate, there might be a negative performance effect because maybe not everything's done in parallel. We could, instead of doing a design change, increase cache size, right, and then thereby decrease capacity misses, right, because of capacity. But as we've talked about, maybe this will increase latency, which I haven't demonstrated that. I'll show that in a second. We could also increase the associativity, so we're fully using, so it's not the mapping that's limited us, right? So again, we decrease conflict misses, but now we have the complexity of finding where it is. This may increase access time. And then finally, if we increase block or page size, right, we decrease compulsory or common misses, right? But now there's an increased penalty for every miss because we have a larger block size. So now we have to read all that in. So this is an interesting price we pay and game we play because of operating in these memory hierarchies, both in cache and in virtual memory at RAM. Let's talk about latency real quick. I wanted to mention this earlier. Didn't get to, I'll mention it here. With drawing information in with latency. So right here are a couple solutions to deal with latency due to drawing information in that it kind of just mentioned in that trade-off presentation, right? Is you have your processor, you have cache, and your bus, and they're all the same width as memory, one word wide. So one word gets spread across the bus, maybe it's 32 bits, 32-bit word, I don't know. Right, and you read it into cache. Cache bus is the same as the processor bus, so everything is driven by the memory 32 bits. But the latency issues, right? Now you're reading just one word at a time. So one solution, like we kind of demonstrated there, was increase your bus size, right? So let's double this, make it 64, or quadruple it, 128. Now we can read 2 words or maybe 4 words of memory at once into cache, and then draw them into the processor. Well, now we have to add the logic here of a multiplexer because the processors may be reading things, each separate CPU core at 32 bits, but the multiplexer's at 64 to 32. So we add complexity and time cost there. The other option, right, is to have memory banks broken up or interleaved, right, and can all be accessed by the bus at any one time. Right, so here's kind of what that looks like. I didn't go over this earlier, so I wanted to mention it there since we were talking about overall trade-offs here right at the end. All right, we have one more thing to cover, and that's everything for Chapter 5. It kind of gives an example. We talked about this already, designing a simple cache controller, cache coherence. So here's the last thing, and then some examples of actual implementation. These are kind of outdated at this point. So a lot of processors today, including the one I'm operating on, right, and maybe this will date the presentation, right, I have an i7, and so this has 4 cores in it, all right, and so essentially 4 CPUs. Well, this introduces another challenge we haven't talked about, which I mentioned earlier in the class in the first couple lessons, but now we're going to go in depth, of dealing with what's called coherence. Because now not only do we have to ensure that cache, RAM, and hard disk all have the same data or instructions whenever one of them are updated. But we also have to deal with inter-CPU coherence, right? Because if each CPU has its own cache, right? If CPU B accesses some array, okay, and updates it, then CPU A and all the memory layer hierarchies need to be updated also. So this gives an example right here, right? So CPU A reads X, okay? So it brings it into cache and it's got a 0, memory is a 0. CPU B reads cache, it's 0, 0, okay? CPU A writes 1 to X. Now look, these two are what's called dirty because this is updated, but these have the, well, memory is not dirty here, but cache B, CPU B's cache is dirty because it has the old state of X, whatever it was. So this is the issue. So now we have to create algorithms to solve cache coherence, and there's all kinds of ways to solve this, right? So 3 of them that it mentions here is multiprocessors that the operations are performed by caches. Excuse me, I'll just read it. Operations performed by caches and multiprocessors to ensure coherence, right? They move the data to local caches or replication of read-shared data, okay? Snooping protocols, each cache monitors the bus read and writes, okay? So they're kind of all in on the loop, so to speak. Directory-based protocols, cache and memory recordings share status of blocks in a directory, so it's almost like a status bank saying who's written what, okay? So cache coherence is something we have to deal with when we have multiple CPU cores. Here's some issues when it comes to invalidating snooping protocols. Some of the challenges, for example, CPU A reads X, so the bus activity, cache miss for X, so 0 is shared, okay. CPU B reads X, cache miss for X, so 0 shared, okay. CPU A writes 1 to X and invalidate for X, so that's the bus activity, so it marks this to invalidate. CPU B read X, cache miss for X, so it has to go get it. So this is kind of what happens when we have to go look for, or snooping example, what it was to keep everything up to date. Here's an example of where that might happen. So for example, Intel 4-core processor, very similar to what I just talked about, right? So you have the cores 0, 1, 2, 3, and then you have their cache. So L1 cache 32 kilobytes. Actually there's a couple of it, so it's broken up, okay? I cache, D cache, okay? So 32 at L1 of I and D, so they broke up instruction and data cache, okay? So they're in they've got them located in 2 different caches, one for instructions, one for data. And then L2 is just combination, okay? But it's half a meg or 512 kilobytes. So you can see that right here. And then what it doesn't list out here is the 2 megs, 8 megabyte L3 cache, which looks like it's broken into 4 banks, 2, 4, 6, 8, 2 megabytes each. Okay, so each of these cores have their own cache, right? And this is all in our effort to keep the CPU or CPUs fed, right, and drive down that CPI. But now look at this. You've got to deal with coherence between the cache in L1 for instructions and data of each, the cache in L2 of each, and then the banks of cache in L3 of each of these 4 cores. So things get interesting kind of fast. Okay. Here are some trade-offs. You can pause and look at this if you'd like. For some examples, A8 versus i7. Here you can see one of them doesn't even have L3, and then it explicitly says A9 only has 2 levels also. And here are some of the performances to consider comparing and how much they use, which cache they use, how much they use it, what the miss penalty is for each of those. And finally, some more comparison on data miss rates, okay, for different specifications. Again, I'm not going to spend a lot of time. You can pause and look at these. And then what about optimizations on these different systems? So kind of putting it all together, right? On-rolling, like I mentioned in Chapter 4. Blocking, like I mentioned here. Other things that may be done to try to maximize the number of floating operations per second in gigs on these different data sizes being pulled in. So you can see it's effective doing all of them. All right, that concludes Chapter 5, Part 2. We covered a lot of material. I went more in depth on what we covered the first time, and I think I filled in any gaps. As always, if you have any questions, please let me know.